All right. So thank you for the invitation and allowing me to speak here. So it's based on joint work with Jakob Hultgren, Jonsson, McCleerey, who are all here, and also Enrica Mazzon. So some brief outline. So I want to get to this optimal transport problem, but the motivation is generating Calabi-Yau hypersurface in the spirit of what Jan Lee has been talking about. So I was to spend some time on this. So some of it might be a bit of repetition, but then it's also partly a parallel story where you don't need this non-Archimedean language. Then I will get to this optimal transport problem that we use to study this and how it can help us understand some regularity issues for this limiting potential. So the motivation is to understand Ricci flat metrics on Calabi-Yau manifolds, and in particular as they degenerate. So just some brief repetition here. Calabi-Yau manifold is a compact Keller manifold whose canonical bundle is trivial. So this is the exterior power of the holomorphic tangent bundle, and it's the dimension of X. And Yau shows us that such manifolds has a Ricci flat Keller metric. And the way you sort of understand this is you encode the metric by its Keller form in this way where J is the complex structure. And if you then fix the class, that also gives you the uniqueness from Yau's theorem, then you can study these corresponding potentials. And then the Ricci flatness is encoded in this complex Marshall pair equation, where omega is the holomorphic volume form from this trivial canonical bundle. So some examples we've seen also from Dan's talk. You can take a hypersurface of projective space of the right degree. The dimension is the ambient dimension is n+1. You should take an n+2 degree n+2 homogeneous polynomial. And you can also do this. You can get families in this way if you vary the polynomial. So for the Fermat family, you take this family of polynomials. So as t goes to 0, you sort of degenerate into this very sort of singular thing which is not irreducible, just a bunch of copies of low dimensional projective spaces. So you can imagine that the metric has to degenerate quite severely. And it's also an example of this large complex structure limit, which Jan told us about. So this you can do a bit more generally. We start with the projective manifold and a section of the anti-canonical, so the dual of the canonical bundle, which shouldn't be, the section should not be 0. Then you can look at the 0 set, and as long as it's smooth, you get a Calabi-Yau. So in this talk, so a version of this will give us the type of family that we study. So the examples that we consider are toric hypersurfaces. So you start with a dosant and reflexive polytope. Dosant I will not talk so much about. Reflexive I will get to a bit later. But it's in particular, it's a polytope with integer or lattice vertices. And then for every lattice point, there's a corresponding sort of monomial on C star to the n+1. So then as a submanifold first of C star to the n+1, you can consider this sort of explicit thing. So you take the monomial corresponding to 0. So it's sort of just a constant function over C star to the n+1. And then you add t times s, where s is some generic section in the space generated by the monomials whose corresponding points are lattice points of this polytope. So the Fermat family is sort of an example when you choose this for a specific s, and for this polytope is a certain standard simplex. So this is not, of course, compact, but this polytope also defines a certain compactification of C star to the n+1. And then this family will be the restriction for each t. You get that this x tilde t is the restriction of something in this compactification, and that will be compact Calabi-Yau. But this sort of gives a very explicit thing if you just work over C star to the n+1. And we also get Kähler classes by restricting the first Schoen class of the ambient space, which will be a Kähler class in this case. Yeah, and as I said, the Fermat case corresponds to a certain simplex. In this case, when t is 0, you I mean the thing is sort of pushed to the boundary of what you're compactifying with, which are some lower dimensional projective spaces if you work with projective space, but then a toric variety you compactify with some lower dimensional toric varieties at infinity. So it degenerates very severely when t goes to 0, and these define these large complex structure limits. Then there's these conjectures that we like to understand. We've seen this weak version of the metric SYC conjecture, which you look at these kind of families, more general ones, but in particular the ones that I've shown. And then you want sort of a large measure subset, a special Lagrangian torus vibration when t is small. There's also a sort of related conjecture, Schulman conjecture, which talks about the Gromov-Hausdorff convergence of these metric spaces. And they're sort of related because, as Young has told us, in the SYC, you imagine these torus fibers to become very small. So you could imagine that the Gromov-Hausdorff convergence should reflect that, and the conjecture is that you obtain something, I mean, sort of converge to the base, which will be real n-dimensional, so you lose half of the dimensions. It says more what sort of structure you should have there. You should have some sort of manifold structure with affine shards of this type. And the metric should be something called a Riemann-Ampere metric, which is a metric induced by the Hessian of a convex function who solves the Riemann-Ampere equation. And there should be something like two codimension 2 singularities of this structure. So this, you have a Riemannian structure on a large subset. There are some singularities. So this is what we like to understand eventually, and now sort of give some brief sketch of a way to try to approach this in this setting. Try to get from these degenerating families to some an optimal transfer problem on the boundaries of polytopes. And we've seen something like this from Young's talk, but here you can of course do the same thing, but here you can also do something slightly different that I would like to showcase. And I should also say that it's also sort of something that Young did in the course of proving weak metric SYC for the Fermat family. So it's sort of very similar. So you consider this log map that we've seen. So the first kind of step is maybe to try to understand the image of the family under the log map. So now we consider the log map on the ambient space. So this is a little bit different from Young's talks. So you look at the image under the log map, and the first step is that you void some set of small Calabi-Yau measure, and this converges in the Hausdorff sense to the boundary of the dual of this polytope. So that's sort of how the dual of the polytope arises. Okay, so now we sort of know, at least for the image, what sort of happens as t goes to 0. And then in the measure, now you want to understand sort of the right-hand side of the equation that we're considering on the family. So this would sort of seem version of from Young's talks as well, that this thing converges to, in a certain sense, to a Lebesgue type measure on the boundary of this polytope. So in the non-Archimedean setting, this plays the role of this essential skeleton, but you see here it plays somewhat of a of a different rule, but you still have this converges then for the right-hand sides. So then, at least on this ambient space, there's this correspondence between Mazzon pairs. So the log map gives you a connection between the real and complex Mazzon pair operators. So then you could have this sort of at this point naive idea that maybe we should try to solve some kind of Mazzon pair operator on the boundary of this polytope with this right-hand side, and then hope that the solution might be some kind of asymptote for the Calabi-Yau matrix. That is some sort of idea that you could have. But so far we haven't really defined what this would mean, so this is part of what I will do. Then, even if you're able to do that, you have to compare somehow the solution with the Calabi-Yau potential. And this you could do in roughly two ways. You could either start using this non-Archimedean package, but here you can also do it in a sort of different way, which is quite concrete. So maybe I should draw something. So on our n+1, we have this polytope, might look like this. And then you can look at the image of the family. These are these things that people studied called amoebas. They look something like this, but as one of the things that was stated there, most of the mass are concentrated close to the boundary of this point. So then, how do you compare? So this solution, even once we've been able to define this equation and potentially solve it, it will live on the boundary of this polytope. So to compare, you might need to extend it in some reasonable way. And once you have done that, you can then pull back to the family and try to compare there. So it turns out you can do something like that, but of course you need to extend it in some reasonable way. I'll say something more about this, and this was some of the approach used by Yang Li in this Fermat case. Okay, so now I want to continue with trying to formulate this equation in a reasonable sense. So the data is really a reflexive polytope. So this is a polytope with integer or lattice vertices. And the reflexivity means also that if you consider the dual polytope is a new polytope where the vertices of the first one plays the role of normals to the faces of the second one, and everything should be normalized so that you have one here. And the reflexivity condition means that this should also be have lattice vertices. So on the boundary of this polytope, so by convention we're sort of working with the boundary of the dual here. This supports a manifold structure. It's sort of singular in the sense that it doesn't cover all of it, but it covers everything except some codimension 2 that we just call singularities. And this will be a very particular manifold structure because it will have transition maps of this type. This can be defined, but it's very non-unique. So this construction I draw. So work with a simplex in ambient three-dimensional space. So maybe this is the dual polytope, so primary polytope is also a simplex. So you begin to try to cover with some shards. So the way you do this is that you do this for each vertex. So you fix a vertex, and the goal now is to define some coordinates around on a neighborhood of this vertex. So what you do is that so the vertex corresponds to a face here, this face, and what's special about reflexive polytopes is that each phase, the space spanned by a phase will have a lattice structure. So that's sort of because the normal is a lattice vector, so you can sort of quotient, you get a lattice structure of this space spanned by this phase. So maybe it looks something like this. So then you choose a couple of points in here. So you choose some M0, kind of reference point. Then you choose n generators of the lattice, if you think about this as the origin. And now you use these to define coordinates. So these sort of define linear forms on this side. So the coordinates that you define look something like this. So you take M1 minus this reference point. So this gives you a linear form. This space. And similar for the other one. So this gives you a map. Which of course we want it to be 1-to-1, which is not going to be on the entire polytope, but it's going to be so. I can show that it's 1-to-1 on the corresponding star of the vertex. Star is the union of facets that contain its vertex. So on there you can define it, and the image will be some sort of triangle in this case. This is the vertex, and then you will have these codimension 1 parts look something like this. Okay. So then you continue, you do this for more vertices. And then you want to, of course, look at the transition maps. So then let's say that this codimension 1 part is identified with this one. Then the transition maps, the transition map will not be differentiable there. So that we have to reduce the size of this sets a little bit. So now comes the choice, which makes this construction non-unique. You have to choose some way of dividing each codimension 1 part into one sort of one thing for each vertex. So in this case, you can just divide by removing some points. And then with respect to this vertex, you also remove everything that's over here, these line segments. So here I will remove, it will correspond to the image of the chart looking something like this. And of course, with respect to this vertex, I now remove this part instead. And if I do it like this, then the transition maps, I will never evaluate them on this codimension. Yeah, so I mean, the transition maps are now only going to be defined on the interior of facets. So they will be differentiable, and they will even be of this very special type. So that's how that goes. It's not unique, and it's more severe in higher dimensions. So you can imagine this is a codimension 1 thing when n is 2. Then when n is 3, it's harder to draw, but codimension 1 will be something like this. So now you have 3 vertices, and you have to divide this into 3 parts, and you could make this in possibly many ways, something like this. And but in a similar way, you get this kind of manifold structure with these singularities. So you should really think that, I mean, as a manifold, this is just the sphere with, in this point, 6 points removed. And then in one dimension higher, you would get something like a sphere with a graph removed, and so on. Okay. So now we have this manifold structure of this very special type. This supports a canonical Lebesgue measure, which you can see in a few different ways, but one is just that you choose it in some chart, and then with these transition maps, it glues together everywhere, and you normalize it. So I would call this nu delta. So you can also define the Riemann-Champère operators if you have these types of charts. So it's well defined as as a volume for example, it's if U is convex and sufficiently smooth or smooth. So this will almost turn out to be the right kind of thing, not exactly, because it's sort of related to the fact that we're trying to capture this Calabi-Yau behavior, and the really fundamental object there is symmetric on a line bundle. So here we're trying to capture this in this limiting setting by just this function. It turns out that the right thing to look at is this sort of thing, where we encode everything by a function, but when computing the dimensional pair, we remove some mu, where u is a chart. So if this is our chart, we remove exactly a function like this. You choose some m here, get some linear form. So this would be my mu, and I can choose this m however I want in this subspace. So this turns out to be the right thing, and it's going to be linear on the overlaps, so it's still well defined, but it's only piecewise linear. I mean, it's going to be non-differentiable on this codimension 1 part. So that's our pair operator, and the partial pair equation that we will consider is now this one. And I haven't yet told you what sort of class of functions we should consider. Clearly, they should be sort of convex in this sense, so that this thing is always convex, but we don't know so much more yet. So what should we do about this class of convex functions? Because so far there are a number of problems. We have not fixed completely the manifold we're working on. We don't really know what sort of a class of functions we should look at. So you can imagine if at least B was fixed, we might want to add some boundary conditions, but we don't really know how to do that. And also from a more geometric viewpoint, the Calabi-Yau matrix depends on the choice of polarization, and this has not really entered into the data yet. So the functions that we'll consider are like this. So it's functions on the boundary that admit convex extensions to the ambient Euclidean space with this sort of growth condition. So the subgradient maps Rm+1 to this primal polytope. So this sort of, if you're from Kähler geometry, you see that this sort of at least solves this last problem, because this is how you encode the Kähler class. So you can even vary the Kähler class if you want, then you will vary this polytope. Doesn't really solve this first problem, but it gives us this class of convex functions, and we don't really have boundary conditions at the singularities, but we have some sort of boundary conditions for these extensions, which are quite popular in transport. So now we could ask, does this lead to anything? And this is what it leads to. So this is from his Fermat paper, which is sort of a bit adapted. But so if you have this setup, and if you can solve this kind of equation in an Alexandrov way for a function which has this sort of convex extension of this type. So here it's actually okay that I only solve it on the open faces. So I don't need this mu in the end. The reason is that the consequence that we want is for this weak SYC, and then we're allowed to remove things that have not so much volume, so we can remove this codimension 1 part. The consequence is that you for this family is that you know the weak metric SYC conjecture, and also a weak version of the Consider-Scholden conjecture. So, of course, the natural question is if you can find such solutions. So in his Fermat paper, the sort of found a solution in sort of different way that we will be doing here. So the idea here is to try to use optimal transport to find such solutions. And this looks sort of maybe reasonable because of this sort of boundary condition here. So let me just give some very quick recap of optimal transport in a setting which will be useful for us. So one setup which is particularly simple and nice, if you have normalized Lebesgue measures on some convex domains, and you look at this, you try to find an optimal transport map. So this is something where constraint is that it should take the first measure to the second one, and you should minimize this type of cost, so sort of the integrated cost of transporting U to U prime with this map. So in this case, there's a nice theory for this, where solution is of the form of the gradient of a convex function. And if you use that and look at this condition, you're led to this sort of motion pair equation. And here, this sort of boundary condition enters naturally. So this is some indication that optimal transport is a good sort of theory for us here. So this is a sort of particularly nice setup. There's some regularity which allows you to know this existence, and you can consider this equation sort of classically. But with less regularity, you might not have something like that. So the best that you have in some very general setup is an optimal transport plan. It's not going to be so important, but what it is Robert mentioned it briefly. I think it's a way for you to be able to split mass. So the optimal transport might not be defined as a map, but you're allowed to split mass. So you formulate this as a probability measure on the products, and this should have the marginals. Marginals should be U and U prime respectively, and then you can consider a similar sort of optimization problem. Try to minimize the cost, and then it's still connected to a convex function. Is supported on the subgradient of a convex function. So that was just some quick recap of optimal transport. But sort of in our setup, there are some things that are a bit similar. We are in the end interested in locally this type of marginal pair equation. Then we have this type of boundary conditions, but in a kind of convoluted way. And we don't have Lebesgue measure on convex domains. It's more like something on the boundary of some convex domain. But still, one can try to consider the following optimal transport problem. So we have the boundary of the dual polytope, the boundary of the primary polytope with these Lebesgue measures, and we use the bilinear cost. So this was first sort of thought of in this paper by Hultgren, Jonsson, Mazzon, McCleerey. And then this is sort of a theorem that we found, which sort of, I mean, you could hope that you simply do this and then find these solutions that gives you a consequence for the SYC, but it's not quite the case. We found this sort of analytic condition which characterizes when you can solve this equation that we wanted. So this is in the end what we want for the application to the SYC. This is our Chalmers solution to pair equation on the. It's enough to have it on the open faces, and then we want this extension property. So this is possible through this optimal transport problem, precisely if you know that the optimal transport plan takes, it should say facet, any facet should be transported into the corresponding star. So in this picture, let's maybe change the rules. So we have transport going in this way. You want this phase to be transported into this corresponding star, and not on the, this case, not on this facet. So that turns out to be something you need. And just what is the reason? The reason is very quickly put to sort of that you need to compare two different notions of subgradients. So when you look at the Alexandrov formulation of the marginal pair, subgradients plays a huge role. So this optimal transport problem is really formulated on the ambient space of dimension n+1. So there you have your subgradient. It's even more convenient to really formulate on the boundary of this polytope with a sort of C gradient, but roughly speaking, it's sort of something to do with the ambient space. There you have one notion of subgradient. But then the actual Green-Marchand-Pair equation, that's more in these coordinates. So there you have a different notion of subgradient, and you would like to compare. And it turns out that you can compare in a good way given this sort of a posteriori condition. Otherwise, the comparison is not good and it doesn't really work. And as we will see, getting a bit tired of myself, but this it doesn't always hold this condition, unfortunately. So it only works sometimes. And sort of how you should think about this is that it's only if this condition is met that the optimal transport problem is really useful for this degenerating Calabi-Yau problem. So for the optimal transport problem has a solution, but it's only useful in this particular cases. And in general, then you would probably have to consider something like this recent, more general optimal transport problem, which then differs from this one. But at least if this condition is met, this one is sort of good enough. And the good thing is that it's very explicit. So some examples. So there are some positive examples, meaning that this first, you can verify the first condition and then you get this nice solution and application to S by C. So there are two sort of mechanisms for these positive examples so far. So one uses discrete symmetry. So it works for the standard simplex that's related to the Fermat family. We also verified it for a certain standard cube. And then Jakob, together with the Boulder Krafft, found a nice sort of class of polytopes, which includes these. They're called reflexive Y polytopes. And the point is just that they have a lot of reflection symmetries. So really the idea here is really to use reflection symmetries. So I thought I would sketch the argument in a very simple case. We consider the cube. So the dual polytope, in this case, I will draw it in the same picture, something like this. Let's consider this one to be the primal polytope. And let's focus on this facet. So then we want to show that this facet is transported to this star. And the idea is to use some reflection symmetries here. So we have a reflection symmetry about this axis. So then you can start think about what happens if I have transport from a point here over this axis defining the reflection symmetry. So let's say it goes over there. That's still allowed, but it's actually not even this will in the end be possible. So what you can use is some sort of this reflection symmetry. I mean, respects this optimal transport problem, and by some uniqueness theorem, you will end up having transport also going reflection symmetric way like this. And this is not possible in this type of optimal transport. One way to think about it is that the gradient of a convex function will not be able to map points in this way. Another way is just that sort of more optimal to transport this to that, that to that. This is not allowed, so the consequence that you end up with is that this is actually mapped to this part, or at least inside this part, and this lies in the corresponding star. So you use some kind of argument like that, and the argument is very similar in all these higher dimensional cases as well. So then there's another mechanism to provide positive examples, which is not relying on this symmetry. So this was this condition found by Yang Li in his paper on this toric hypersurfaces. So I think he mentioned it. The condition is just that you should not be able to find vertex pairs which have pairing 0. So that's also a sufficient condition. But then there are also plenty of negative examples. So the mechanism here that we found to produce a lot of them is that sometimes this condition that we want isn't even satisfied on the level of mass. So I mean, that gives you clearly a necessary condition. This is sometimes not satisfied. So the question is now what can you do more with this optimal transport problem. It sort of gives you SYC in some cases, but nowadays, as we have learned, we have sort of established it, Yang Li established it very generally. So one thing I want to talk about here is that this optimal transport problem can teach us more about the solution. So this would then be useful if you assume this extra condition, so that it really says something about this degeneration of Calabi-Yaus. So what are the sort of things that you might want to know? You might want to know some regularity, so in particular some interior regularity away from the singularities. There's also this problem of the affine structures. So you sort of avoid this in this weak metric SYC by just removing everything of codimension 1. So then you have sort of in some sense dealt with the problem, but you might want to know, I mean, in the Conservi-Shulman conjecture, they really conjecture that there is some location of the singularities of codimension 2, which the Calabi-Yau metrics really give you. So there is that problem. And then maybe also some more regularity, like what happens close to the singularities, so on. So we use this optimal transport problem to say something about this. So the first thing is related to the second point, this singular tropical structure. So we have this ambiguity of precisely specifying this affine structure, choosing the location of these singularities. So one idea could be that now you have this solution. There's sort of a uniqueness. You could wonder, does the solution tell you what the singularities should be? I mean, the idea is somehow that you want to extend the solution, and maybe you can extend it precisely outside the singularities in some sense. So we do something towards this. So we define some closed set so that on the complement, this Marchand-Ampere equation is still solved on this set. So this is now outside of these open faces. What is this? Well, heuristically, it's this sort of thing. So you look at the codimension 1 part of the boundary of this polytope. And T here is supposed to be the optimal transport map. It doesn't always exist, so this is a little bit heuristic. But if it would, and it would sort of be 1-to-1, it would be something like this. So you now consider the codimension 1 part of the boundary of the primal polytope, and you move it to the boundary of the dual polytope with the inverse of the transport map. So that gives you something, and we're able to show that outside of this set, Marchand-Ampere equation extends. I mean, the solution extends to something solving the Marchand-Ampere equation. There's still a lot to do here, so we don't know very much about this set in particular because it's a bit more complicated. So it's really something like the C gradient of the C transform, which might not be single valued. So in the end, it's a little bit more complicated. So some things that one might want to know is something like, is it of codimension 2? And you would also like to know if it's minimal. I mean, can you extend the solution further, or is this really the end of the story? And to that end, we have some varying answers. So in general, the answer to the first question is no. So what might happen you can find some very particular examples. So there is an example, actually still a simplex, but it's sort of a simplex where with this correct Lebesgue type measure that we're working on, there's one facet which has a very large mass. And it is so large so that the mass of this facet is exactly the same as the mass of this corresponding star. So what does that mean? Because the mass is the same, then you might want to draw the consequence that it's mapped precisely on the star, but it could, of course, map also outside the star. But this example also satisfies Yang Li's condition. So this thing where you cannot have vertices that pair to zero. And then he proves that there is this solution to this North-Ampere equation. And then by our theorem, it has to actually map phase inside of the corresponding star. So as a consequence, this phase is mapped slightly onto the entire star. And as a consequence, the boundary of this facet is then mapped sort of here. So then when you take the intersection, of course, you would no longer have codimension 2. So that's what the intersection of this set, you would like this to be sort of a good intersection, but in this type it's a bad intersection. So the answer here is, in general, no. So it's a little bit unclear, but we give some kind of guesswork or indication that in precisely this case, it might also not be minimal. So in this case, you might also be able to extend further to, in the end, get codimension 2 singularities. But this is a little bit, this is not really worked out because it sort of depends on knowing something more about the optimal transport map. Some sort of regularity you need to make that argument go through. So in general, this seems to be a little bit intricate, but at least in some examples, this works relatively well. So it works quite well for the standard simplex. So then we can compute this set, it's codimension 2, and it's minimal. And for the simplex, we could do quite a bit. So for the simplex and also the cube, in any dimensions, we find the set where the solution extends. It's a codimension 2, and we also have a regularity theory for the solution on this set. So it's completely smooth. So let me discuss that. So maybe let's start with this setup. So this is one example, very low dimension. But from this symmetry argument, we could find that if you recall that this facet is transported to this part of the boundary. And in this case, they have exactly the same mass. So that sort of gives you that this facet is transported to really exactly this entire thing. So that gives you quite a lot of control. So, of course, that was in very low dimension. So let me draw what happens for, say, the simplex, one dimension higher. So you do something similar. You use symmetry to argue exactly where this phase is going. It's going to something which looks like this. And again, they happen to have the same mass, so that gives you a lot of control. So first of all, that tells you something about these singularities. So now you know where, this codimension 1 part is now transported to this one, so you can compute the intersection. Yes, this midpoint of the edges. And then to get the regularity, you go to the coordinates. So this will be something like a hexagon. And this is just a triangle. So now you're studying an optimal transport problem of the type that I discussed, which is very sort of standard. So now you have Lebesgue measures on these convex domains. And then Caffarelli's theory gives you regularity. So sort of do this slowly, but everywhere, and you get regularity outside of the singularities. Okay. Right. So one can sort of wonder. I posted these questions about the regularity, but what are they to be used to? So this has some applications also for the SY3 conjecture. So like in this simplex case corresponds to the Fermat family. We know this weak metric SYC. But this sort of thing yields a slightly stronger version. So what is weak metric SYC about? You have your family, and then you have this, this case, this polytope, which is supposedly sort of the base of this SYC fibration. But in the weak version, you only care about this in the subset of large measure. So you have this SYC fibration on a subset of large measure. But this subset, in the conjecture, there is not saying anything, I mean, explicit. It's just something. And in this case, I mean, for example, if you use a non-Archimedean approach, you have to remove, at least currently, these codimension 1 parts. You will also have to remove sort of the potential singularities of the solution to the real Marshall-Ampere equation. So you use some kind of generic regularity, and then you just remove everything else. So in the end, sort of the set, I mean, this set is very sort of abstract. So in this setting for the simplex, we get some sort of stronger result. So it's actually enough to remove the singular set. So in this picture, it is the midpoint of these vertices. So then you remove some closures, some open sets surrounding these, and then you can guarantee the SYC fibration on the remaining parts, making T sufficiently small. So it gives sort of a more explicit version of the weak metric SYC, and it's sort of as good as it gets as long as you want to stay in this sort of semi-flat region. I mean, we're not really imagining that this semi-flat approximation really works close to these singularities. So this is sort of as good as you can get in that sort of regime. So that's one motivation to obtain this sort of regularity. And the same sort of argument works for this class of reflexive white polytopes. So you use this sort of symmetry. So you can also wonder about further regularity. So this is promoted by this Concevius-Soldman conjecture. So the Concevius-Soldman conjecture says that the metric that appears in the limit is really the Hessian of this convex function. Or in this case, really the Hessian of this u minus this mu. So it defines the Riemannian metric where it is smooth, and you get a corresponding distance function. And conjecturally, it's the metric completion of this thing that should arise to Gromov the limits of this Calabi-Yau. So it's motivating to try to study this. So one wants to describe the completion. So this is what we started doing in this second paper. So in that case, we work with the standard simplex. We got the following thing. So, I mean, this B, this part outside the singularities, it also has this sort of Euclidean metric. So you can consider the identity map where you use this Riemannian metric that you get from the Hessian of U. And then we get some sort of result here that is solid continuous and extends. The point is really that it extends to sort of continuous surjective map when you include, I mean, for the Euclidean part, you consider the entire polytope, and then you take the metric completion. So sort of the moral of the story here is somehow that when you take the metric completion, you're not adding more than what is already in this polytope. So that's one thing that you might want to know. So how do you do this? It's exactly the same sort of, it tries to use as much as possible of this existing regularity theory for real Marshall-Ampere. So you still sort of reduce to this setting, which in my example would be this, like the angle to this hexagon. And Caffarelli has this regularity theory, and then you try to understand what does it give sort of geometrically for this metric, and this is something you can get out of it. So some for the further problem is that you might want to know that this is injective, so that somehow the Euclidean metric really describes the metric completion in some topological way. And because we could show that fibers are connected, this is okay for D. Should be N equals to 2, but we don't really know the general. So, okay, one slightly quicker. Let's see if I want to say something. So maybe we go to an extra slide. So we also did something. We had Yang talk about this sort of metric mirror symmetry, where we try to actually bring mirror symmetry into the mix here. So in this setting, mirror symmetry is approximately like exchanging the role of the dual and primary polytopes. And in this optimal transport setup, you get a map between these. So it's really given by this sort of C gradient, where C is the cost. So we prove some regularity of that, also sort of over the singularity. So it's a bijection, and it sets up an isometry on this regular loci, and this is sort of expected. I mean, a local version of this has been a part of SYC. I mean, in the semi-flat case, you use sort of Legendre transform to pass between two affine structures, but it's really like the same Riemannian metric. But here we get some kind of global variant of this. And when n is 3, there's not to draw, but of course, when you work with a simplex, the dual is also a simplex. It's not the same reflexive simplex, but they're affinely equivalent. So you have this map from sort of one of them to the other, but then you can just affinely identify them, so you get a map from the simplex to itself, which is an isometry on this smooth part. So I want to say something about this positive and negative vertices that we saw. So this is something, so now it's try 4 simplex, but it's something like this. So also in this case, I mean, we find this singular locus. So in this case, codimension 1 is a simplex, and the singularity is that you divide them in this way, in this sort of the only symmetric way. So you divide each simplex like this. So, and then you have to continue, right? But the singular set is some kind of graph. The graph has some vertices, and there are sort of 2 types. So there will also be one type where I mean, this is one type, and then there will also be another one. So let's see if I can draw this. This is another one. This is sort of the same type, but there will also be one type where you move up here. So you see here, you also get something which is slightly different because it lives on this edge. So I mean, there are ways to detect differences between these 2 kind of vertices in this graph. So these are these positive and negative vertices. I don't remember exactly which is which, although potentially this is the positive one and this is the negative one. But something that we found here is that the metrics actually looks the same around these points. That's sort of just something that comes out of this, which is a little bit curious. So somehow, even though the metric behavior of the Calabi-Yau is supposed to be quite different from this perspective, it's sort of not so much of a difference. So lastly, I would just like to give some kind of summary. So there is sort of a lot of potential for further progress. So we sort of know a lot for this Fermat family, and the same sort of things work for its reflexive Y polytopes. So there, the optimal transport problem is very explicit. Maybe I should also say that, I mean, if you want to understand the behavior close to these singularities, the local kind of optimal transport problem is something like understanding what happens. So locally, it looks like a half space on one side, and it looks like a quadrant on the other side, and you like to understand what happens close to here. So if you can understand that very well, you understand the singularities of this metric as well. So that we don't know so much about yet, but you have an explicit optimal transport problem, so you can sort of consider such problems. But then we have the interior regularity, we know the affine structure, and we have at least a partial understanding of the metric completion. But as I mentioned, we don't know so much about sort of more precise singularity behavior. So then for a reflexive polytope where you assume this optimal transport condition, then you know that you're sort of working with the right optimal transport problem. It's completely explicit. One way to know this condition would be to assume Yang-Lee's condition. So there, things are a bit more complicated. We have no regularity theory, and we know these examples where the affine structure has some extra intricacies. And then in general for toric hypersurfaces, this optimal transport problem, as we've seen, is not really the right one. So you might have to go to this more general, much more general setup of Yang-Lee, but then it's not as explicit. But I think in the next talk, we might hear something about that. Possibly it could still be somewhat explicit in this case. And then, of course, in general case, we know that there is an optimal transport problem, but not so much more. All right, thank you.